We are going deep into the world of quarks.
Quarks.
The tiniest particles that make an atom look gigantic.
Yeah.
You wanted to understand these fundamental pieces, these building blocks of matter.
Absolutely.
And I've got to tell you, there is so much more to them than you might think.
Oh, yeah.
We're talking some seriously weird, seriously cool stuff.
It's going to blow your mind.
Yeah. Get ready to have your mind blown, because we're going to cover all 6 flavors.
Flavors?
That's right. That's what scientists call them. Up, down, charm, strange, top, and bottom. Scientists have a sense of humor, I guess.
They do.
Yeah, so we've got 6 flavors. What else makes a quark a quark? Do they have like a personality or something?
Well, yeah, I mean, I guess you could say that. Each quark flavor has its own properties.
Okay.
Its own distinct set of properties, kind of like a personality. Like they have different masses, electric charges. Some even have a fraction of the charge of an electron.
Really?
Can you believe that?
Wow.
And then they have something called spin.
Spin.
Which is like their internal rotation. And it's these properties that make each quark flavor so unique.
So it's like each flavor brings its own special dance move to the party.
Yeah, the subatomic party.
Right. But hold on, I read something about color charge too.
Color charge.
Are we talking about rainbow quarks here?
No, not exactly. Color charge, it isn't about actual colors.
Okay.
It's more like a force property.
Right.
Think of it like positive and negative charges.
Yeah.
But instead of 2, there are 3.
3
types. Red, green, blue.
Oh, interesting.
And it's this color charge that allows quarks to interact through the strong force.
Now, the strong force, that's one of the fundamental forces of the universe, right?
It is.
The one that holds the nucleus of an atom together.
That's it. That's the one.
Yeah.
And it's this strong force that leads to one of the most intriguing things about quarks.
Okay.
They can't exist alone.
Ever?
Never. They're always found in groups bound together by gluons, which are particles that carry the strong force.
Oh.
So it's like they're in this cosmic game of tag, constantly exchanging these gluons.
So quarks are like the ultimate social butterflies. They always got to have their friends around.
Always.
But if they're always hanging out together, how do we even know that they exist?
Right. Well, we can't see quarks directly.
Yeah.
But we have some clever detective work that proves they're there.
Right.
One way is through deep inelastic scattering.
Okay.
Imagine shooting tiny bullets at atoms to see what's inside.
Right.
By analyzing how those bullets scatter, we can actually infer the presence of quarks and even learn about their properties.
So we're playing atomic billiards to uncover the secrets of these tiny particles.
Basically.
Pretty ingenious. But wait, if the strong force keeps quarks bound together, how do they form those larger particles, like protons and neutrons that we find in atoms?
So protons and neutrons are what we call hadrons.
Hadrons.
Which are particles made of quarks.
Okay.
So, for example, a proton is made of 2 up quarks and 1 down quark.
All bound together tightly by the strong force.
So it's a tiny little inseparable trio.
A little family.
Yeah. Okay, so protons and neutrons are made of 3 quarks each.
Yeah.
Are there any other combinations out there?
There are.
Yeah.
Absolutely. There are also particles called mesons.
Mesons. Okay.
And those are made of a quark and an antiquark pair.
So
it's a bit like a antimatter tango.
Antimatter tango.
But we'll save that dance for later.
Okay.
We'll save that one for now.
Now that sounds intriguing. All right, so we've covered the basics. Quarks come in 6 flavors.
6 flavors.
They have unique properties, and they always hang out in groups to form hadrons.
Right.
But I have a feeling that things are about to get even wilder.
Oh, yeah. Buckle up.
Welcome back. Last time we were exploring the wacky world of quarks,
right.
Their flavors, their color charge, and how they always have to be bound together by the strong force.
They do.
But then we hit this real head-scratcher.
Yeah.
Asymptotic freedom.
Asymptotic freedom.
Asymptotic freedom.
In extreme conditions, like the early universe, it's like the rules get thrown out the window.
It's true. At extremely high energies, quarks act almost independent, like they're not bound by that strong force. It's like, a cosmic dance where the partners suddenly decide to freestyle.
Okay.
And this leads to the formation of something called Quark-Gluon plasma.
QGP.
Or QGP for short.
The QGP, that super hot, super dense state of matter that existed just after the Big Bang.
Right.
I mean, it's pretty mind-boggling.
It is.
And we established that scientists are recreating this QGP in particle accelerators, like the Large Hadron Collider.
We are.
But what are they learning from it?
Oh, it's a fascinating area of research.
Yeah.
I mean, think about it. We're recreating the conditions of the early universe right here on Earth.
Here on Earth.
By smashing heavy ions together at incredible speeds.
I see.
we create these tiny fireballs of QGP,
Okay.
allowing us to actually study its properties, how it behaves.
I'm trying to wrap my head around this. If we can't even see quarks directly,
Right.
how do scientists study this QGP?
Right.
It's like trying to analyze the ingredients of a cake just by looking at the crumbs.
Well, you're not wrong. It's a challenge.
Yeah.
But scientists have developed really sophisticated techniques
Okay.
to analyze the particles that escape from these QGP fireballs.
Well-
It's like a detective investigating a crime scene,
Okay.
They piece together the clues from the evidence left behind.
I see.
So by studying the trajectories and energies of the particles that emerge,
Okay.
scientists can learn about its temperature, density, other key properties of that QGP.
So they're using these particles as messengers from the early universe,
Exactly.
carrying information about the QGP's secrets.
Exactly.
That's pretty cool. But wait, we talked about quarks always being bound together to form hadrons?
Right.
Do these hadrons also play a role in the QGP?
Yeah.
Or are they completely broken down in this extreme environment?
That's a great question. And it gets to the heart of what makes QGP so interesting. Because in the QGP, those boundaries between individual hadrons,
Uh-huh.
they can become blurred.
Okay.
You remember those mesons we talked about, the
Yeah.
quark-antiquark pairs?
Yeah.
They actually play a crucial role in understanding QGP.
Okay, remind me why mesons are so important again.
Well, they're not just these cute little quark couples, right?
Right.
They help us understand how the strong force works at different energy levels.
Okay.
Remember, the strong force is responsible for binding those quarks together,
Yeah.
but it also acts between hadrons themselves.
Yep.
And mesons, they're key to understanding this residual strong force,
Uh,
which governs the interactions between protons and neutrons in the nucleus
Right.
of an atom.
I see. I'm starting to see the connection here.
Yeah,
So by studying how mesons form
right.
and behave within the QGP, we can get a better understanding of the strong force under these extreme conditions.
Exactly.
But why is that so important? How does this connect back to the big picture?
Because understanding the strong force is fundamental to understanding how the universe evolved.
I see.
I mean, in the early universe, this force shaped the first protons and neutrons,
Right.
which eventually formed atoms, stars, galaxies.
Wow.
By studying the QGP, we're essentially studying the building blocks of the universe.
That really puts things into perspective.
Yeah.
These tiny particles and their interactions have huge implications for understanding the grand history of the universe.
It's incredible.
It really is amazing how something so small can be so significant.
It is.
But let me ask you this.
Yeah.
If quarks can exist freely in the QGP, could they also exist freely in other extreme environments?
Right.
Like, are there other cosmic places where the rules of confinement might be broken?
That's a great question, and it leads to some of the more speculative ideas about quark matter.
Okay.
Some scientists believe there might be other exotic environments where quarks could exist in unusual configurations. Like, for example, deep inside neutron stars,
Neutron stars.
where the density is so extreme that the boundaries between individual neutrons might actually break down,
Really?
leading to a kind of quark soup.
A quark soup inside a neutron star.
Exactly.
Now, that's something I'd love to see.
That's wild.
But if these extreme environments can liberate quarks like this, it makes you wonder, could we ever manipulate quarks directly here on Earth?
Right?
Could we create new materials or unlock new energy sources by harnessing the power of these fundamental particles?
Those are big questions,
Yeah.
and scientists are actively exploring them.
Yeah.
While we're not quite at the point of manipulating individual quarks, understanding their behavior and interactions could lead to breakthroughs
Yeah.
in fields like material science,
Right.
energy production. Who knows what the future holds?
I guess that's the beauty of science, right?
It is.
There's always more to discover, more mysteries to unravel.
Always.
But for now, let's just pause and appreciate the incredible journey we've taken so far.
Yeah.
We've gone from the basics of quarks to the mind-boggling concept of QGP. And even ventured into the speculative realm of exotic quark matter.
It's been a wild ride.
It has been a wild ride, but we're not done yet.
Not even close.
All right, we're back for the final part of our quark adventure. We've covered a lot of ground flavors, colors, those crazy gluons, and even that wild Quark-Gluon plasma from the early universe. But before we wrap things up, I feel like we need to delve into some of the more mind-bending mysteries surrounding quarks.
Oh, absolutely. There's still so much we don't know, which makes it all the more exciting.
Exactly. So where do we even begin with the unsolved mysteries of quarks? I mean, we've talked about the standard model of particle physics, which seems to explain a lot, but I get the feeling there are some cracks in that picture.
You're right, the Standard Model has been incredibly successful in describing the fundamental particles and forces, but it does leave some big questions unanswered. One of those is the hierarchy problem.
Okay, the hierarchy problem. That sounds ominous. Break it down for me. What's the issue?
Well, it has to do with the masses of different particles. Specifically, why is there such a huge difference in the masses of the different quarks? I mean, the top quark is something like 170,000 times heavier than the up quark.
Wow, that's a pretty big difference.
It is, and the Standard Model doesn't really have a good explanation for why there's such a wide range. Some physicists think there might be new, undiscovered particles or forces at play that we haven't accounted for.
So it's like we're missing some pieces of the puzzle when it comes to understanding quark masses.
That's one way to think about it. And this mass hierarchy problem isn't just about quarks. It also affects other particles, like the Higgs boson, which is responsible for giving particles mass in the first place.
Right, the Higgs boson. I feel like we could do a whole deep dive just on that topic.
Oh, for sure. It's a fascinating particle. But getting back to quarks, there's another big mystery that's really captivating physicists. The connection between quarks and dark matter.
Wait, dark matter? I thought that was a whole other realm of cosmology. What do quarks have to do with it?
Well, we know that dark matter makes up a significant portion of the universe, but we still don't know what it's made of.
Right, it's like this invisible, mysterious substance that we can only detect through its gravitational effect.
Exactly. And some theories suggest that dark matter particles might interact with quarks through forces that are beyond the Standard Model. It's a bit like there's this whole hidden world of particles and interactions that we're just beginning to glimpse.
So quarks could be the key to unlocking the secrets of dark matter.
They could be a crucial piece of the puzzle. There are experiments underway right now that are searching for signs of these interactions between dark matter and quarks.
It's mind-blowing to think about, really. We've gone from these tiny particles that make up protons and neutrons to mysteries that could reshape our understanding of the entire universe.
It's a pretty amazing journey, and it's a testament to the power of scientific inquiry. We keep digging deeper, asking questions, and trying to understand the fundamental nature of reality. And who knows what incredible discoveries await us in the years to come.
That's what makes it all so exciting. It's like we're standing on the edge of a vast, uncharted territory, and quarks are our guide. So to our listeners out there, keep exploring, keep asking those big questions, and who knows, maybe you'll be the one to uncover the next big breakthrough in our understanding of these fundamental building blocks of the universe. And on that note, thanks for joining us on this deep dive into the world of quarks.